In this video, we'll be discussing the determination of shear strength of soil. There are different tests for finding the shear strength of soil. They are direct shear test, triaxial compression test, and confined compression test, vane shear test. In this video, we'll be discussing direct shear test only. See, the shear tests are conducted in two stages. First stage is consolidation stage and second stage is shear stage. What do you mean by consolidation? We have studied that soil consists of soil solids, air and water, isn't it? So if you take a soil and apply compressive load, which component will be coming out first or which will be escaping first? Air will be removed first, and when compressive load is applied, air is removed and the volume of the soil is reduced. If I again apply load, the air will be escaped completely, and if I again apply load, what will happen? The water will come out. Okay. So if water is coming out and the volume is reduced, then that process is known as consolidation. So what is consolidation? The reduction in volume of soil by the removal of water is known as consolidation, and it is a very slow process. Okay. So when shear test is conducted, the first stage is consolidation stage. In that stage, water should be coming out. Okay, so drainage should be provided for consolidation. Okay, and normal stress or confining pressure is applied in that stage. Second stage is the shear stage. In that stage, we'll be applying the shear stress or the deviator stress. Okay, now based on the drainage conditions provided in these two stages, we have three types of shear test. One is unconsolidated undrained, then consolidated undrained and consolidated drained. Okay, so you can see that there are two words. First word corresponds to the drainage condition in the first stage, that is consolidation stage. Here in this stage, consolidation will occur only when drainage is allowed, then only water can go out. So if in the consolidation stage, if drainage is allowed, then the first term will be consolidated. Okay, so in this test, drainage is not allowed in the stage 1. In this one and this one, drainage is allowed. So the first term is consolidated. Okay. Now in the second term refers to the drainage condition in the stage 2. In shear stage, if drainage is provided, then the second term will be drained. If drainage is not provided, then it will be undrained. Okay. So we'll discuss these tests in detail. Yeah, here in unconsolidated undrained test, drainage is not provided in the consolidation stage as well as shear stage. No drainage is provided in the consolidation stage and shear stage, and this can be done very quickly in a few minutes. So this is also known as quick test. Okay, and it is UU test. U from here and from here. So it is UU test. Now the second type is consolidated undrained. So here in the consolidation stage, drainage is provided. Drainage is allowed in the consolidation stage. Okay, it is allowed to consolidate. So first term is consolidated. Now in the second stage, that is in the shear stage, drainage is not provided. So undrained. Okay. Now here this one is known as Q test and the third one is known as S test. So in between you have the alphabet R. So this test is known as R test also. Now in this test, if pore water pressure is measured, then this test is known as CU bar test. Okay. Now the third one is consolidated drained test. Here drainage is allowed in both the stages, in consolidation stage as well as in shear stage, drainage is provided. So after consolidation only we will be applying shear load, and this is a very slow process. This is a very slow test. So it is known as S test, and here excess pore water pressure is not developed. We are allowing drainage in both the stages, so excess pore water pressure is not developed, so it is 0. Okay, so this is regarding the three types of shear test based on the drainage condition. Okay, now Based on mode of application of shear force, we can have two types of test. One is strain controlled test and the other is stress controlled test. Okay. Now this is based on the shear application. Shear can be applied either by increasing the shear displacement or by increasing the shear force. Okay. In some tests, we will be increasing the shear displacement. Okay. We will be increasing the shear displacement given to the soil specimen. In some cases, we will be increasing the shear force applied to the soil specimen. So, based on this, we have two types, strain control test and stress control test. In strain control test, we will be giving the shearing strain at an increased rate. Okay, we will be increasing the shearing strain or the shear displacement at a given rate. And in this case, the force is measured indirectly using something known as a proving ring. We cannot measure force directly because we are giving shear displacement. So, shear force can't be measured directly. So, we will be indirectly measuring the shear force using a proving ring. Okay, and in this type of test, stress strain characteristics are easily obtained and we can observe the stress strain curve beyond the peak value also. Beyond the failure point also we can observe stress strain curve, and this one is very easier to perform when compared to stress controlled test. Okay, now coming to stress controlled test, here shear force is increased at a given rate as I already told you, and shear displacements are obtained from the readings of dial gauge. In all the cases we will be using a dial gauge for measuring displacement. Okay, now this is preferred for conducting test at a very low rate. That is, if you have to control this shear force increase, then we can go for stress control test. And if you want very accurate result and if you want to closely represent the field conditions, if you want results which will be obtained in the field itself, then you have to go for stress control test. Okay, so that is strain control test and stress control test. We will be mostly doing strain control test because it is easier to perform. Okay, so that is based on mode of application of shear force. Now we'll start the first test, that is direct shear test. In direct shear test, we'll be using something known as a shear box. Okay, so this is the shear box. Shear box is split into two, the upper half and the lower half. In the lower half, you can see two handles, two curved handles are attached to the lower half, and a U-frame, an inverted U-frame is attached to the upper half. Okay, so this person is trying to put the upper half on the lower half so that it will form a box. Fine. So after keeping the upper half on the lower half, this thing is known as shear box. Now after keeping upper half on the lower half, we will be putting locking screws at these two holes. See here you can see these two holes, right, diagonally opposite. So through this hole you will be inserting a locking screw. This is a locking screw or locking pin. This will be inserted at this hole and at this hole. So it will be extended to the lower half also. What is the purpose of using this locking pin? See here we will be filling soil inside this box. So while filling the soil, these two halves should not be disturbed. That is the purpose of locking screw. So first step is to insert the locking screw. These two are the locking screws and they will be inserted at this point and at this point diagonally opposite. Okay, then we'll start the soil preparation or sample preparation. First you have to keep the base plate. This is the base plate. So initially base plate will be inserted and then you will be keeping the grid plates. Okay, these are the grid plates. One of the grid plate will be inserted above the base plate. Okay, see here I am explaining the setup for an undrained test. In this case water is not allowed to go out. Okay, I'll tell you how to do what is the change if you are conducting a drain test. So this is for undrained test. So first you have to keep the base plate, and then you have to keep the one of the grid plates, and here on the grid plate you can see grooves like this, isn't it? Linear grooves. These grooves should be perpendicular to the direction of shear displacement applied. If you are applying shear in this direction, the grooves should be in this direction, perpendicular to that. Okay. So one of the grid plates will be placed, and then on the top of the grid plate you will be filling the soil, and after filling the soil you will be keeping the second grid plate, and then on the top of the grid plate you will be placing the loading pad. On the top you will be placing loading pad, and on the loading pad you can see a steel ball, and through this ball the normal stress is applied. Normally in the downward direction you will be applying a stress in addition to the shear stress. So that normal stress is applied through this steel ball downwards. Fine. And finally, just before keeping this shear box in the setup, we will be keeping spacing screws on the top, and this is not extended to the lower half, it is just on the upper half. Okay, so on these three holes will be keeping spacing screws. Fine. So this is the setup. After the soil preparation or after the sample preparation, this shear box will be looking like this. You can see everything. This is the lower half. To the lower half the handle is attached. To the upper half this inverted U frame is attached, and on the top you can see the loading pad, and here you have the spacing screws, and these are the locking screws. Okay, now what I will do is I'll take this shear box and I'll keep it in a shear box container. Okay, just before applying shear deformation I'll be removing these locking pins. If locking pins are there, it will not shear off. The deformation will not be occurring, because this pin is connecting both the halves. So first we need to remove these locking pins in order to conduct the test. What is the purpose of locking screws? They are just for holding these two halves together while filling the soil. Okay. Now shear deformation will be applied to the container in which shear box is kept, and the proving ring will be connected to this inverted U frame. Fine. Now I told you that this setup is for undrained condition. If it is a drained condition, then you have to follow this order. First we will be placing the base plate, and then you have to place a porous plate or porous stone, and instead of that solid grid plate you have to use a perforated grid plate. A perforated grid plate is with holes in it. There will be holes in the perforated grid plate, and on the top of that you have to place the soil specimen. Then you have to use again the other perforated grid plate, and then porous stone, and then loading pad. So here the only difference is the addition of porous plate, and also a perforated grid plate should be used. This is the setup for a drained test. Okay, so this is the shear box filled with soil. Now this soil will be taken and it will be kept in this blue box. Can you see this blue box? This box is known as shear box container. Inside this you will be placing the filled shear box, and will be giving shear deformation to this container, and the lower half is placed on this container. Okay, and the upper half is free to move. So as the shear box container is moved in this direction, the lower half will also move along with the container. Okay, and the upper half will stay where it is, and the upper half is connected to this U frame, and this U frame is connected to the proving ring. This is the proving ring. From this proving ring reading we can find out what is shear force. And here you can see a dial gauge. From dial gauge you can measure the vertical displacement, and if you keep a dial gauge over here you can measure the horizontal displacement also. So from dial gauge readings you will be getting the displacement values, and from proving ring reading you will be getting the shear force values. Okay, so this is a motor. So using this motor you will be giving shear deformation to this box. Along with this container, the lower portion of the shear box will also be moving, but the upper half will stay where it is, and from this you will be getting the shear force readings. See here, you can see the setup for giving the normal stress. I told you that along with shear stress, normal stress is also provided. It is provided in the downward direction vertically. That is provided using this setup. Okay, here you will be putting weights and that will be transferred in here. Okay, so this is the setup for direct shear test. So this is the procedure. Procedure is given in the notes provided in the ERP also. Two halves are there. They are held together by locking pins. Then soil is filled in the shear box. Grid plates are placed. It is filled up, and then box is kept in the position for setup. Then just before starting the test, locking pins are removed. The lower half is fixed in position. Upper half is touching the proving ring, and then normal load is applied. Then shear load is applied at a constant rate of strain. The rate used for undrained test and drained test are given over here for sandy soil and for clay soils. Then shear displacement is measured using dial gauge. Proving ring readings are also taken, and these readings are taken till the specimen fails. How will we know that the specimen is failed? See, if the proving ring reading is rotating in the opposite direction, then we'll know that the soil is failed. So you have to take reading till the proving ring reading recedes. Okay, and after failure, the test specimen is removed, and then we'll be repeating this test for different normal stress value. In the downward direction, we are giving a normal stress value. That normal stress is not changing during the test. Okay, so once one cycle is completed, one test is over, we'll be doing the same test with the different normal stress value. Okay, so this is how test is conducted. Now about the results. As I told you, we'll be getting the shear load from the proving ring value. So shear load by cross-sectional area will give you your shear stress, and you can from the dial gauge you'll be getting the shear displacement. Shear displacement by length of the specimen will give you the shear strain, and also you can find out the normal stress. Normal stress value is not changing during the test, so you can directly get the value of normal stress. So results will be represented based on these values. Okay, now representation of shears, representation of the results. First one is stress strain curve. See, this is the stress strain curve. On this axis you have the strain, and this axis you have the stress, and we can plot the values. Okay, now if you are conducting test on a dense sand, this will be the shape of the curve. There will be a peak value, and then it will decrease like this. Okay, if you are conducting the test on a medium dense sand, then this will be the curve. This will be the shape of the curve, and if you are conducting a comparatively loose sand, then this will be the curve. Okay, so that is the stress strain curve, and there are some additional curves also. If you are plotting the strain with the volume change, then we can say that for dense sand initially the volume will decrease and then increase. For loose sand the volume will be decreasing like this, and for medium dense sand this will be the trait. Okay, this will be the condition. Now there is something known as critical void ratio. If you are plotting strain with void ratio, then we find that for a loose sand initially, if it is loose, then again the void ratio will be decreasing with increase in strain. Okay, now if we are conducting test on dense sand, then the void ratio will be increasing like this. Okay, so if void ratio value is over here, then that soil will also show a similar trend. Okay, so you have a critical void ratio ECR where even if the strain value is increased, the E value will not be changed. So for that type of soil, if the value of void ratio is critical void ratio, then the curve will be a straight line like this. Okay, even if there is increase in strain, void ratio is not changing. So what is critical void ratio? It is a void ratio at which there is no change in void ratio with an increase in strain. So that is critical void ratio. Now the second representation of result is using failure envelope. We already have studied what is a failure envelope. So how to obtain this? As we have studied in the first representation was using stress strain curve, right? So here we have the stress strain curve. On this axis you have the strain, on this axis you have the shear stress, and here we are conducting a number of tests on the identical specimen for different normal stress values. Okay, so here this curve is for normal stress sigma 1, this curve is for normal stress sigma 2, and this curve is for normal stress sigma 3. So three types, the test is conducted 3 times and we are getting 3 curves. Okay, from the first curve we can obtain what is the shear strength, what is the shear stress value at failure. From second curve also we can find out what is the shear stress value at failure. From third curve also you can find out what is the shear stress value at failure. Okay, so you will be getting sigma 3 corresponding to tau F3, sigma 1 corresponding to tau F1. Okay, so you got sigma and tau values. So how many points you will be getting? You will be getting 3 points. If you plot a sigma tau F curve, you will be getting 3 points. Okay, if 4 samples are tested, then you will be getting 4 points. These points can be obtained, and join these points to get the failure envelope. This is the failure envelope. Okay, we have studied that the inclination of the failure envelope with the horizontal is nothing but phi, your angle of internal friction phi, and the intercept on the tau F axis is the cohesion C. So from this failure envelope you can obtain phi value and C value. The shear parameters can be obtained from failure envelope. So this is how you get failure envelope from direct shear test values. Okay, now the third representation is using a Moore circle. Okay, see here in this case the failure plane is fixed. Always the soil will fail only in the horizontal direction, isn't it? So one lower half will be moving in one direction, upper half will be moving in the other direction. So always the soil sample will fail in the horizontal plane. So the horizontal failure plane is fixed. So we can draw a single Moore circle at failure condition for the horizontal failure plane. So you got the failure envelope and you will be getting a point which represents the shear tau value and sigma value at failure. So that will be B. From that point draw a perpendicular to the failure plane. So this red line is perpendicular to the failure plane. Okay, so this red line will cut the sigma axis at point C. With C as center and BC as radius, you can draw the Moore circle. Okay, so this is the Moore circle. Now how to get the minor and major principal planes? From B, draw a horizontal line because the failure plane is horizontal, isn't it? So we'll draw a horizontal line and this horizontal line will meet the Moore circle at point P. This point is known as pole. We have studied about pole in the previous video. So as the failure plane is horizontal, if you draw a line from B horizontally, then that line will meet at the pole, meet the Moore circle at the pole. Now from the pole, join PA. See, point A represents the minor principal stress, isn't it? So if you join A and the pole, then this will be the minor principal plane. Similarly, point D represents the major principal stress, and if you join P and D, this will be your major principal plane. So graphically, if you are solving the problem, you can find out from the test data you can draw the failure envelope, and from one of the points, from point B, you can draw BC, you can find out C. At C, you can draw the Mohr circle, and from the Mohr circle, you can get the inclination of major and minor principal plane. After getting Mohr circle, you can find the value of principal stresses also. So these type of problems are asked for university exam. So in those questions, you need to first draw the failure envelope. You'll be getting a point P. So from point B, you can draw the failure envelope, and then once you get the failure envelope, you can draw a perpendicular like this. You'll be getting the center of Mohr circle, and from that center, CB as radius, draw the Mohr circle, and then the ends of the Mohr circle will touch the sigma axis at 2 points, and those 2 points will give you the minor principal stress and the major principal stress. You can draw this in a graph and you can measure these values. Once you measure these values, you'll be getting the major principal stress sigma 1 and the minor principal stress sigma 3. And also you can find out the orientation of major and minor principal planes. Just join the pole P and this point, you will be getting the minor principal plane. Measure this angle, you will be getting the orientation of minor principal plane. Now join the pole and this point, you will be getting the major principal plane, and measure this angle, that will be the orientation of major principal plane. Okay, so here you can see that this is the major principal plane, right? So this is the major principal plane. On this major principal plane, sigma 1 is acting. Similarly, this is the minor principal plane. This is the minor principal plane. On the minor principal plane, sigma 3 is acting. And this is the failure plane, horizontal. So this is the failure plane. This is the lower box and this is the upper box, lower half and upper half. So this is how you represent the results of direct shear test. Okay. Now, what are the merits of direct shear test? As we have seen, the sample preparation is very easy. The test is also very simple and convenient. Okay. And if you compare with other shear tests, the thickness of the sample is relatively small. So, if you are conducting a drain test, it is very easy to perform a drain test as there will be quick drainage as the thickness is very small. It is ideally suitable for drain test on cohesion-less soil. That means soils like sand. It is very much suitable for direct shear test is very much suitable for soils like sand, which is cohesion-less. Okay, so direct test is usually conducted on sands only. So it can be used for clay soils also, but it is usually suitable for cohesion-less soil, and the apparatus is relatively cheap. These are the merits of direct shear test. Merits and demerits are asked for the university examination. So please remember these points. Now, what are the demerits of direct shear test? First one is that we are aware of the stress conditions only at the failure. Just before that, we don't know what is a stress condition. So we have a clear idea about the stress conditions only at the failure. And stress distribution on the failure plane is not uniform. We know that the failure plane is horizontal, and the stress distribution, it is not uniform. We have corners, so at the corners there may be stress concentration. So stress distribution on the failure plane is not uniform. And the area of the shear is gradually decreasing as the test progresses. We know that it is a square, and as the lower box and the upper box or lower half and the upper box are moving, the area is reduced. Area of contact between the lower and upper halves are reduced, isn't it? So as the test progresses, the area of shear is decreasing. And area correction, we have no provision for applying any area correction, so that is a disadvantage. Now we know that failure plane is fixed. Failure plane is always horizontal, and that horizontal plane may not be the weakest plane. So that is a disadvantage. It is very difficult to control the drainage conditions. It is difficult to control the drainage conditions, and for measuring pore water pressure, we don't have any provision. So these are the demerits of direct shear test. So we'll be discussing the problems based on direct shear test in the coming videos. Okay, thank you.